Math 1314, Tyler Junior College, Section 3.3, Dividing Polynomials, Remainder and Factor Theorems. All right, we're finally going to get to one of the theorems alluded to in the title of this section, the Remainder Theorem. In order to naturally let it develop instead of just saying, here it is, let's recall one of the division problems from the previous video. We had worked 5x to the third power plus 6x plus 8 divided by x plus 3 using synthetic division, and the quotient was 5x squared minus 15x plus 51 plus a remainder of negative 145 on top of the divisor x plus 3. I'm going to take some of the pieces of this problem and pose a new problem. Suppose f of x equals 5x to the third power plus 6x plus 8, which was the dividend in this problem. Let's evaluate f of negative 3. Now, what did negative 3 have to do with this problem? If you recall the synthetic division problem from before, this was the box number because it was the opposite of the number in the divisor. So let's evaluate this and see what we get. Hint, it's a number that we've already seen. If we evaluate f of negative 3, we need to substitute negative 3 for each x. So we'll get 5 times negative 3 to the third power plus 6 times negative 3 plus 8. Negative 3 to the third power is negative 27. So let's go ahead and do the exponent. Everything else stays the same. And now let's multiply. 5 times negative 27 is negative 135. Yep. Positive 6 times negative 3 is negative 18. And then the plus 8. Well, the negative 18 and the plus 8 combine to make a negative 10. So negative 10 and negative 135 is negative 145. Wait, we've seen that number before. Where was that number? That was the remainder in the division problem. Remember? So it kind of makes us go, wait a second. What? Why did that happen? Why did substituting negative 3 into the function give us a value that matched the remainder? Or was it just a coincidence? Obviously, if it was a coincidence, I wouldn't be dwelling on it right now. So the better question is, why was the function's value, when evaluated at the opposite of the divisor number, equal to the remainder? The answer is a little unclear unless you remember how to check a division problem. Remember how to check a division problem? For example, if I said that 23 divided by 5 is 4 3/5, which it is. Or let's just say 4 remainder 3. I know that's not the way we're writing remainders, but let's say that it is. How can we check that the correct answer to this problem is 4 remainder 3? You check by multiplying what you divided by times your quotient and then adding the remainder. So 5 times 4 gives me 20, plus the 3 gives me the 23 back in return. So how would we check this division problem? If we claim that this divided by this is this quotient and this remainder, then if we wanted to check it, we would say that the divisor, which was x plus 3, times the quotient, which was 5x squared minus 15x plus 51, plus the remainder, so plus negative 145, is equal to the original dividend. Now, we would have to multiply all this out and gather like terms, but if you trust me, it will give us the dividend. But that's what we call the function. So in this problem, we can rewrite the function not as the dividend, but as the divisor, in this case x plus 3, times the quotient, in this case 5x squared minus 15x plus 51, plus the remainder, so plus negative 145. And now you see why substituting negative 3 into this gave us negative 145. Negative 3 is the number that made the divisor equal to 0. So putting a negative 3 here will turn it into 0 times something, but it doesn't matter what that something is because it gets multiplied by 0. And then after that, we add the negative 145. So it's not a coincidence that substituting negative 3 into the function gave us a value to match the remainder, since negative 3 was the number that made the divisor equal to 0. But how can we generalize this? In other words, if you make an observation and you think it's true all the time, then how would we write that? The answer is pretty simple. And it's called the remainder theorem. The remainder theorem. Make sure I'm consistent with one thing real quick. Yeah. If f of x is a polynomial, and the theoretical mathematician in me is asking, must it be a polynomial? But let's not go outside of those boundaries for now. If f of x is a polynomial, then the remainder of f of x divided by x minus c, and there's a reason we're saying x minus c, is, think about what we would put into the function. The number we put into here was the number that made the divisor equal to 0. So if we have a divisor in the form x minus c, what would I have to replace the x with so the subtraction problem is equal to 0? I'd have to put a c here. C minus c is equal to 0. So the remainder is equal to the function evaluated at the number that makes the divisor equal to 0. Now, is this worth doing? Why can't I just plug the number directly into the function? Well, you can, but it really depends upon the magnitude of your function. For example, let's say that f of x is equal to x to the 5th power minus 4x to the 4th power minus x to the 3rd power plus 9x to the 2nd power plus 11x plus 10, and I ask you to evaluate, let's say f of, I don't know, hope this doesn't get too out of control, but it doesn't matter. Let's say I ask you to evaluate f of 3. Well, we can substitute the 3 in there, and then we have to do an exponent, an exponent, an exponent, an exponent, and then a multiplication, a multiplication, a multiplication, and then finally combine all the terms. But in synthetic division, all you do is add, multiply, add, multiply, add, multiply. So those are our options. A lot of powers in the correct order, a lot of products in the correct order, and then finally combine like terms, or just oscillate between adding and multiplying. The work in synthetic division is actually a lot more smooth in my opinion. So how would we set up the synthetic division problem to do this according to the remainder theorem? Well, it's a little tricky to keep track of everything, but when you see it set up, it's actually pretty easy. If we're going to plug a number into the function, then x minus that number would be the divisor. But when we set up the division problem, we take the opposite of the number in the divisor. What's the opposite of negative c? C. To use the remainder theorem, all you have to think about is this. To evaluate a polynomial function, you have two options. Put the number into the function, or put the number into the box. I'm going to put the number into the box and set up the top row. No missing terms. Again, the reason the sign doesn't change is because it actually changed twice. When this input goes into the divisor, it changes signs, but when the divisor creates the box number, it changes the signs again. So the sign gets changed twice, which means the net result is it doesn't change at all. All right, I'm going to go through this at my normal speed, but it depends upon how big the numbers get. You may have to go slower or use a calculator. I will call out my moves. Bring down the 1 times 3, add to get negative 1 times 3, add to get negative 4 times 3, add to get negative 3 times 3, add to get 2 times 3, 16. Let me double check our work. 1 times 3 is 3, negative 4 plus 3 is negative 1. Negative 1 times 3 is negative 3, negative 1 and negative 3 is negative 4. Negative 4 times 3 is negative 12, 9 and negative 12 is negative 3. Negative 3 times 3 is negative 9. 11 and negative 9 is 2. 2 times 3 is 6. 10 and 6 is 16. Therefore, f of 3 is equal to 16. Is that the same answer we would get if we substituted 3? Yep, except I didn't need to worry about 3 to the 5th power, or 3 to the 4th power, or 3 to any power. I just had to add, multiply, add, multiply, add, multiply until I got to the end. So think of the remainder theorem, and some people call it synthetic substitution instead of synthetic division. We are synthetically substituting 3 into the function by instead running it through synthetic division. The remainder will be the functional value.